Hello, and welcome to Chapter 2, Section 4. Today we are talking about measures of variation. So when we talk about variation, this is kind of basically asking how spread out is our data. So how much does our data vary, like variation. So to describe how spread out is our data, we have several ways to do this. The first and easiest way to talk about how spread out our data is the range. So range is something that you've been finding since elementary school. The range is when you take the biggest number and subtract the smallest number from it, and that'll just tell you what the distance is between like your highest and lowest point. So because the range is just finding the biggest number minus the smallest number, this is a great way to tell how far apart your data is. However, it only takes into account two numbers in your data set, which isn't very much because what happens with the rest of your numbers we don't actually know. So another way to talk about variation or spread is then called the deviation. So this is a little bit more specific than the range because we're actually going to compare how far each data point is away from the mean. So that means we have to calculate the mean of the whole data set first. And remember, the mean kind of tells us where the center is. So if you know the center, then we can compare each of the data points away from the center to see what that distance is. So to calculate that, we take each data point and subtract the mean from it. So the deviation, you'll get a bunch of numbers that tell you how far each data point is away from the mean, which is helpful because then it kind of tells you like if some of your data points are really far from the mean, if some of them are very close to the mean. So in order to kind of summarize this, we use something called the standard deviation. So the standard deviation is basically the average distance away from the mean. So if we found all the deviations and took the average of that, then that would give you the standard deviation. So then we know like each of our data points is about this far from the mean. So the formula for standard deviation looks a little crazy. So first we have to find all our deviations. So to do that, we took our data point, subtracted the mean from it, and then because sometimes depending on what your mean is, when you subtract, sometimes you get a positive number, sometimes you'll get a negative number depending on what the data point is and how big it is compared to the mean. We want to square that number, so each of the deviations will square it, because when you square something, it makes everything positive. So we end up with all these positive numbers, and then remember this symbol here means to add everything up. So the sum of all our squared deviations, and then we're going to divide whatever we get from adding it all up by either n or n minus 1. So it depends on the situation, and we'll talk more about this. But n just stands for how many total data points do you have. Once you've divided, you square root the whole thing, and that's your standard deviation. The reason why we square root the whole thing is to like kind of cancel out the squaring that we did earlier, because we ended up with all positive numbers. So that's why we want to have that square root there. If we did this whole calculation without the square root, that's actually called the variance. So basically, the variance is the average squared distance away from the mean. So if we did this whole formula and it just left out the square root, that would actually be the formula for the variance. Or if you already knew the standard deviation, you could just square it and that'll give you the variance. So coming back to our standard deviation number, our final standard deviation, whatever we do after we do our calculations, you're going to get some number. And that number basically tells you like how spread out is your data on average. So if you have a smaller number for your standard deviation, that actually means that your data is less spread out, because everything then is like kind of close to the mean, because closer to the mean means a smaller distance, so standard deviation is smaller. If your standard deviation is a bigger number, then that means each of your data points is farther away from the mean, because then that distance is greater. So greater distance from the mean means greater standard deviation. So I want to kind of compare and contrast. I've made 3 graphs here. So they're all dot plots because I just want a really quick visual here. So looking at all of these dot plots, all 3 graphs or all 3 data sets are all symmetric because they're the same on the left and the right side. They're mirror images. But looking at all these graphs, because they're all symmetric, the mean is always going to be the same as the median, and that's going to be right in the middle because they're symmetric. So for each of these graphs, the mean, the average, is always going to be 5 for each of these data sets. But because each of my data sets are spread out differently, each of the standard deviations here are all going to be different. So this first graph that I have, all the points in my data set are all 5s. So that means in my data set, I only have number 5s in it, which means that if they're all the same number, they're not spread out at all. So in this case, the standard deviation, when all of the numbers are the same in the data set, the standard deviation is going to be 0. Because if the mean is 5 and all the data points are 5s, then the distance between the data point and the mean is 0. Because if you found the deviation, the data point minus the mean, you would get 0 every time. So that average distance is 0. But then looking at our second graph, now we're a little bit more spread out. So most of our points are still where the mean is, because we said the mean was 5. We have 5 points that are on 5, but then we have 6 points that are close to 5, but not quite. So that standard deviation there is going to be not 0, because 0 would have to be where every single data point was the same number. But here it's going to be kind of small because our data points aren't very spread out, especially compared to our third graph, where if our mean was 5, we don't actually have any data points in our data set that is the number 5. Everything else is either smaller than it or greater than it. So for the second graph, the standard deviation here is actually 1.2 if you actually calculated this out. But I just wanted to show you guys so that you can compare. If you have kind of points that are close to the mean, your standard deviation is going to be a smaller number. Versus for this third graph, if all your points are kind of farther away from the mean, then that standard deviation, that average distance away from the mean, is going to be a bigger number because it's more spread out. So in the third graph, the standard deviation is actually 3. So now you can compare if you have the different shapes of your data points and how spread out they are, then you can see the standard deviation, how it changes. So now let's actually calculate the standard deviation. Because the formula looks a little crazy, the process for it is a little crazy as well. So I've tried to break it down for you as much as possible. So I have it kind of where you can just fill this out. So we're talking about, 10 graduates from college or whatever, and this is the salaries that they started at in thousands of dollars. So here are all our data points right here. So there are 10 of them. What we want to do is to find those deviations. So first we need to calculate the mean from our 10 data points. So I went ahead and did that. I added them all up, divided by 10 because there were 10 data points, and I got 41.5. So to calculate everything, I'm going to use this little table to kind of organize my work. So first column here, I just have it labeled as X. That's really our data points. So each of our data points, we call it X. I'm just going to list those in each of those spots there. So after just taking each of my data points and putting it on the table here, the next column, this is where I actually find my deviation. So remember, the deviation formula was take each data point and subtract the mean from it. So for this first one, my data point was 41, and I'm going to subtract the mean of 41.5 from it. And when I do that, I get negative 0.5. I'm going to do this with the rest of my data points. So my second deviation is going to be 38 minus my mean of 41.5, and I get negative 3.5 from that. And I'm just going to keep subtracting our mean of 41.5 from the rest of my data points. Okay, so then once I have all my deviations, if we follow our formula that we had for our standard deviation, we wanted to square all our deviations, and then once we've done that, then we're going to add them all up. That's what that symbol, that E symbol, means at the front. So we're going to square all the numbers that we just got and then add everything up. So for my first deviation squared, negative 0.5, when I square it, I get 0.25. And remember, when you square things, you always end up with a positive number. So everything in this column should be positive. Negative 3.5 squared is 12.25, and so on. So we keep squaring. So I've just gone ahead and squared everything. So now I just want to add everything together. So adding up all my squared deviations, I'm going to get 88.5. Okay, from here, once I've added up all my deviations squared, then once I divide either by n or n minus 1, because that's what the formula has, and depending, and I'll tell you which one you divide by, then that'll give you your variance, because variance is the entire formula without the square root. And so once we divide, that's the variance. Once we divide and then square root it, that'll give me the standard deviation. Okay, so here's how we tell whether we divide by n or by n minus 1. So with the variance and the standard deviation, there's actually two different formulas. That's why you either divide by n or divide by n minus 1. It depends on what kind of data set you're given. So if your data set comes from a population, then you're going to divide by n. If your data set comes from a sample, then you're going to divide by n minus 1, because this is different. Remember, a population is like everyone you're trying to study, but then a sample is just a small amount of the population, so that subset of your population. So that's why the formula is different by a little bit. So remember, n stands for how many total data points there are. So let's pretend for now that our data set is from a population. So this would be something like a corporation hired 10 graduates in total. So these are like all the new hires. So if this was the case, then we would take that 88.5 that we got when we added up all our deviations squared. We would divide by 10 because we had 10 graduates total. So when we do that, 88.5 divided by 10, we get 8.85. So that would be the population variance. Now let's pretend that our sample, or our data set came from a sample. So let's pretend like this corporation hired a bunch of people and they just looked at 10 of the new hires. So if this was a sample, then we would divide by 9, because n minus 1 would be my 10 total in the data set. Subtract 1 from that to get 9. So 88.5 divided by 9 would be 9.83 repeating. So I'll just round it to 9.83. Okay, so that's my variance. So I'm not quite done yet with standard deviation because we still need to square root that number that I just got for the variance. So for the standard deviation, if this was a population standard deviation that I'm calculating, then I'm going to take my population variance and square root that. So my population variance would have been the 8.85. Square rooting that gives me 2.97 if I round to 2 decimal places. Okay, if this was a sample standard deviation that I was trying to calculate, then I would square root the 9.83. And I would get 3.14 if I rounded to the second decimal place. So as you can see, depending on the population or the sample, the numbers change just a little bit. So that's why you have to be careful and read carefully. So in the problem, it should say whether the data set came from a sample, or if it doesn't say sample, then we can assume it's from a population. So I know this process was kind of long to calculate the standard deviation. So obviously we have tools to help us out. So this graphing calculator that we've been using, if I enter all my data set into my list, so remember that's our favorite button, stat, go into edit, enter all your numbers, so you should have 10. Once you have everything entered, we can get our calculator to calculate our standard deviations for us. So we're going to hit our favorite button again, stat, and then go over to the right until you see calculate is highlighted, and then one var stats. So remember, we use this to find our mean and median as well. So the list is where we want to type in like what list we have all our data points in. So I put everything in L1. Freak list, I'm going to leave blank. You don't need anything there. Go down to calculate and hit enter. So again, that first number that it gives you is the mean of your data set, which was 41.5. That's true, we calculated that ourselves as well. And then when you go down to where you see SX, SX stands for a sample standard deviation. That's that 3.135. So we rounded that to 3.14. That was our sample standard deviation number that we got at the end. The number right underneath it, it's like an O with a hat. An O with the hat x, that's the population standard deviation. So it's read as sigma. That O with a hat is read as sigma. 2.97 is what we got as well for the population standard deviation. So the one for our stats will just tell you right away. And remember, if you scroll down, that'll give you your min, your median, all that good stuff, which is kind of nice. Okay, but I did want to show you how to find it the long way, because then it kind of gives you a better idea of how to use the formula itself. If your calculator ever busts on you, then you can still do it. Or if you don't have a graphing calculator, then you would have to do it the long way. The last part of our notes for today, which is not the end of this section, but I'm kind of splitting this up because it's a longer section again, is the standard deviation for group data. And last time we talked about the mean of a frequency distribution, so this is what that is, the standard deviation for a frequency distribution. So in last section in 2.3, when we calculated the mean of the frequency distribution, this is actually the same example. So that was the one where we had to take all our x's times our frequency, so the f's, divided by all our frequencies added together. So x just stood for the midpoints. We had to use midpoints in order to calculate the mean of a frequency distribution. So with this problem, we'd find the midpoints first by taking each of our class limits, adding the upper and the lower class limits together and dividing by 2. And so for our midpoints of the 29 to 33, we would get 31. For the 34 to 38, if we added 34 and 38 and divide by 2, we would get 36. And continuing on, I get 41 and 46. So those are all my midpoints of the class limits. Then my frequencies, I'm just going to list these out so that they're easy to get to. But before we can calculate the standard deviation, because our standard deviation is like the distance away from the mean, we would also have to calculate the mean of this frequency distribution first. So kind of like basically what we did last time was we use this formula. So we're taking each of our midpoints, multiplying by the frequencies. Then we're going to add all those together. So I'm just going to do this really quickly. If you want more detailed steps on how to find the mean of a frequency distribution, I'm going to refer you to the 2.3 video that I made last time, and I'll link it down below. So when I multiplied each of my midpoints and my frequencies together and then added up all those products, I ended up with 1,085, and then I'm going to divide by all my frequencies added together, which came out to 30. So overall, my mean of this frequency distribution ended up being 36.2 if I rounded to one decimal place. So now that I have the mean, I can start calculating my deviations for each of these numbers. So for my deviations, I'm taking my midpoint and subtracting the mean from it. So for the first midpoint of 31, I'm going to subtract my mean of 36.2 to get negative 5.2. And then my next one, I would take the 36, subtract the 36.2 to get negative 0.2. And continuing on, I end up with 4.8 and 9.8. Okay. So the next part of my formula, I want to take all my deviations and square them so we get all positive numbers. And finally, we're going to multiply all those squared deviations with our frequency. So squaring the negative 5.2 for my first deviation, I end up with 27.04. And then I get 0.04, 23.04, and 96.04 when I square all my deviations. And finally, I'm going to take each of those squared deviations and multiply it by the frequency. So that was this F column here. And these are the numbers I end up getting. So once we do all that, following our formula, we want to next add all these up. So we're going to add up this column, and then we're going to end up dividing by n minus 1. So remember, n stood for like the total number of data points that we have. And we don't have like a list of data points here. We have like a bunch of frequencies. So if we add up all our frequencies, that's going to tell us how many total data points we had. So when I added everything in this column, I got 824.2. And then when I added all my frequencies together, I got 30. So n minus 1 would have been 29. These two numbers get divided. So in the end, I'm going to square root this 824.2 divided by 29, which ends up being 28.42, so square rooting that, I end up with 5.33, and that's my final standard deviation of this frequency distribution. Alright, so that's all I wanted to get to for part 1 of this section 2.4. I'll see you next time for part 2. Bye!